Okay, so the Winchcombe meteorite fall, you probably heard about it. This is a scientific analysis of the fall. It was recorded by many amateur networks, and this is kind of like a report of what can be done from a scientific perspective and what are some best practices if we are performing such an analysis. So just a little bit of background. The Winchcombe fall is definitely the meteorite fall of the year, happened in February, and the remarkable thing is that it was a sea chondrite, a very rare meteorite type, and it was recovered very quickly, only 12 hours after the fall. The main mass actually fell on a driveway of one family near Winchcombe, and it recognized it as a meteorite, bagged it, put it in the fridge. So it basically came in no contact with water, which is one of the most pristine examples, together with some pieces from Tagish Lake. Okay, so the meteorite fall itself was observed by basically all fireball or meteor networks in the UK. They have many kinds, I think 6 different kinds of networks observed this particular fall. So I kind of, when that happened, I got roped into reconstructing the accurate trajectory and performing the scientific analysis. And they sent me the original measurements. I computed the trajectory, and you can see the results on the right-hand side. I wasn't particularly happy with that. You can see some errors of hundreds of meters or maybe up to a kilometer, and I wanted to do better. So we were able to obtain all data, or all raw data recorded by all cameras, to perform a much more accurate analysis. Okay. Here's a list of all available patients, and there are some that were used for the analysis, and there were some that were not used for the analysis due to various reasons. We used most of the DFN cameras, or the Global Fireball Observatory cameras, which are nice high-resolution all-sky cameras. We only used one WATEC-based UFO systems. And because they were actually, it was just so bright, there was a lot of CCD saturation and blooming, and we couldn't really get a good centroid. We used most of the Freepond cameras. The quality there was amazing. They're 10-bit cameras. They didn't really saturate at all. We get really good centroids, really good calibrations. And we end up using 2 global meteor network cameras that observe the fireball. Now, of the ones that were not used, I kind of used very strict quality cuts. We didn't use one DFN camera because the fireball was observed in a tree. We didn't use one Freepond camera because there were some frame drop issues. And most of the WATEC systems, just simply because of this blooming, there was just this offset from the center of the fireball of up to 5 pixels. And usually I'm looking for like a sub-pixel precision. We also didn't end up using the All-Sky 7 data. They seem to have a lot of compression artifacts. And there was a dome distortion that just couldn't be calibrated, but I'm going to talk about that later. And we didn't use one GMN camera just because the geometry was terrible. The fireball was literally going into the camera, so they had very little trajectory information there. Here's the example of the good data, quote unquote, because again, we had so much data to choose from. I only took the best one. The upper left corner does the DFN image. Upper right corner is the WATEC recording. And here, the fireball was so far away and wasn't really that much saturating that there wasn't any blooming. So that could be used for astrometry. The Freepond I was able to use it basically throughout. And the DFN, the bottom right corner, that's the Global Meteor Network camera, which just by amazing luck, it was installed literally the day before the fireball, and it was pointing in the right direction. You can even see that it's not properly focused. That was only done after the fireball, but it caught just the right, caught the ending, and from that we were able to estimate like the final mass distribution. It wasn't even properly configured. You can see that even the whole fireball wasn't detected; it was just the end. Okay, and here's the bad data. Again, quote unquote, we're just so spoiled with good data that we could pick and choose, right? So upper right corner, the fireball was in the tree, and because the way DFN does their timing, you couldn't really do the time without the proper like gaps, and because of the branches, you couldn't see them. This Wilcott camera, you can see that the fireball is extremely bright, even though you think, oh, it might be here in the center. It was shifted by up to 5 pixels, which is just ridiculous. A lower left corner, we see the All-Sky 7 camera, and it suffered from some compression artifacts, which really made the The position pick's really hard. There were also some, again, issues with the calibration in terms of the dome distortion. I tried many distortion models, but couldn't really get the high precision that I was looking for to be, let's say, within maybe 0.3 pixels. I was always getting in errors that are much higher than that. And the bottom right corner is that bad geometry GMN station that just, the fireball just looked like a bright blob and then just went away. Okay, so once you collect all the data, we have the SkyFit software, open source, anyone can use it, where we load in this data. It supports all data types of most networks. So the first thing you want to do is you want to pick your stars, do the astrometry calibration, make sure that's very nice and tight. You can see the fireball actually in the lower right corner. And the most important thing to inspect is your astrometry calibration. You want to make sure that in the region where your fireball is, so here around azimuth like 210 and elevation of below about 20 degrees, that your astrometry fit is tight. And here it definitely was. The astrometry errors were on the order of like 0.6 arc minutes, which translates to about 20 meters at a range of 100 kilometers, which is really nice. Okay. So next slide shows what we have to do in the next step, and that is manual data reduction. So if you really want to achieve the kind of the science grade precision, you have to go in and manually pick every meteor. This is the DFN data, or if you're working with video data, you just have to do it in every single video frame. Takes a lot of work, but it's definitely worth it because in the end you get something like this. So we see the height versus the total deviation. So now instead of having a 1 kilometer error, we're getting something on the order of like 50 meters or below 100 meters. And on the right hand side, you can also see a very decently smooth deceleration, which you can use later for dynamical modeling, for fragmentation modeling, to figure out the density and physical properties of this body, which is incredibly important. And also, interestingly, that the Global Meteor Network camera that observed the end, it was showing a large deviation at the end. And that is definitely not due to astrometry, because this is deviation of like up to, let's say, like 10 pixels, but the astrometry calibration was much better. This is actually real. There's like a transverse component to the velocity that was gained after one final fragmentation here, which is also observed for other fireballs. And this is very important to observe in terms of searching for meteorites. If you want to predict where your strewn field is, you have to know if a certain rock deviated from the main trajectory. We estimated the radiant in the orbit quite well. Now, one thing is that I can't really share all the details. It's still a work in progress. It's going to be published in a paper, hopefully in a couple of months, up to a year. But we were able to estimate all the orbit and the trajectory basically better than most instrumentally observed meteorite falls, which is exactly what we wanted to do, because that way we can take this rock and put it in a solar system context. So instead of like sending a space probe to sample an asteroid, well, you have this space rock that's now being analyzed at the National History Museum in London, and we can figure out where it came from. So that's the whole purpose of this work. So with this, we're trying to solve the mystery of where C chondrites come from, or at least the CM2 chondrites come from. The current theory is that they come from C or B type asteroids. And now we're able to add one more data point for that. And it looks like that the orbit matches well to other CM2 chondrites, but we still have to do like a dynamical study. One interesting thing is that when you compare it to all other instrumentally observed meteorite faults, the Winchcombe is the smallest. So the initial mass was about 66 kilograms, while every single other C chondrite fall was over a ton, even tens of tons. And the reason is that in those cases, there's just so much mass that something survived on the ground, something had to survive. With Winchcombe, though, just because the initial speed was small and because the initial entry angle was quite shallow, it was kind of slowly descended onto the ground, and out of 66 kilograms, about 500 grams was able to survive and was found on the ground. And what we've seen with from the optical observations of the last part of the fireball, we can see 4 fragments, with basically 3 to 4 fragments. That's basically how many were found on the ground. So there probably aren't any more fragments on the ground. I think all of them were found. Okay, so I talked about this endpoint. observed from one geometric camera. So why is that important? Well, it was able to observe the fireball until magnitude +3, which is quite faint. You can see the last video frames here at the bottom. And the final observed velocity was about 3 kilometers a second. Why is that important? Well, basically, that is the ablation limit. If the fireball decelerates more than that, it will not produce any light. So this is a strong indication that there's a meteorite fall. And you can take the deceleration observations from the last part of the fireball and figure out what the predicted mass on the ground is. So, and also it was observed 7 kilometers lower than lower sensitivity all sky systems. And this basically helps you pinpoint exactly where the last point on the fireball was and to better estimate the strewn field, so you know where to search for meteorites. So that's why low elevation coverage with sensitive cameras is quite important. For example, in the UK, this is the current status of the GMN coverage at the height of 25 kilometers. Again, if you're operating an all sky camera, that's not really a problem because you're observing down the horizon, but you don't really have the sensitivity. So that's why you have to deploy kind of more sensitive cameras lower down. And the next step was the photometry. So if we want to know the mass and we want to know how the fireball fragmented, which is really important to figure out its physical characteristics, you need to know the photometry. So FreePon is great because it has like 10 bits and it's not very sensitive. And in this case, that's actually great because it's not saturating down to magnitude -8. But after that, it did saturate. So we had to do like a little trick where like a relative brightness was measured off this reflection here that you can see. And then that was scaled up to match the FreePon part. And that's how we were able to reconstruct the full unsaturated light curve. Once we have that in hand, and once we have the dynamical information in hand, we can employ a full meteoroid ablation and fragmentation model and basically figure out how it fragmented into how many pieces, and what is the strength of the body. And that's exactly what we did here. That's how we derived the initial mass. And also the dynamics are very consistent with the bulk density of about 2,000 kilograms per cubic meter, which matches really well for C chondrites. If you have like an ordinary chondrite, you would expect something like 3,500. So this is really good. It matches also well with the meteorite finds. And what we can also tell from that is how it fragmented in the atmosphere, which is really important if we want to probe the structure of the initial body that entered the atmosphere, not just the meteorites that we have on the ground. So when we compare this to other meteorite falls, we can see that this actually it had the lowest peak aerodynamic pressure of all instrumentally observed and modeled fireballs. What this basically means that it was entering the atmosphere, the air was literally pressing on the meteoroid, and the pressure was not too high to completely crumble it, but it actually never reached more than about 0.5 megapascals. If we compare that to other fireballs, we can see that they have like kind of two modes of fragmentation. In the first part, they fragment around 0.1 megapascal, and they lose just a little bit of their mass. And then they don't fragment at all, and they fragment again around 1 megapascal. So in this case, just because of the favorable geometry and speed, it never even reached this 1 megapascal threshold, and that's why it basically survived. Otherwise, it was a bit faster, or if it was a bit steeper, what would happen is that we would get a very bright fireball penetrating down to maybe 35, 40 kilometers, and at the end, there would have been a really bright flare and no meteorites. So with this increased coverage and more fireball networks observing, we're finally able to kind of probe that very interesting population of very weak meteoroids that we were not able to observe before. So the main takeaways, just to conclude, this is the smallest instrumentally observed carbonaceous chondrite that survived atmospheric flight to date. We were able to derive the orbit very accurately, and multi-camera observations were extremely important, simply because we could choose the best data. So for example, if you look at, let's say, Flensburg or other C chondrite falls, if you look what the Czechs did, they had to use like dash cams and security cameras, and it's just not as accurate. But here with the let's say such an amazing coverage they had in the UK, we're able to do a really good job. Now, in terms of what we need more, definitely more sensitive cameras with low elevation coverage that can help to constrain kind of the last part to see where the meteorites fell, and also more ways to observe the unsaturated light curve so we can figure out the initial mass. Here, we're just very lucky to have the free pond data and to also have that reflection. Otherwise, it would have been really tricky. We had to probably do some sort of saturation corrections, and that is not nice. One way is to deploy like cheap radiometers that can, they don't really observe the fireball itself, but just the total brightness of the sky. And then if a fireball happens, you basically just take whatever above the background, which is really nice. And also we need more accurate manual measurements of fireballs if we want to do these scientific studies, or at least some sort of way like of collaboration and data sharing if an interesting event happens. So we can inform our scientific models and the scientific knowledge of the solar system through these observations. Now, a couple of things to avoid. This might be a bit controversial, but definitely the old 8-bit CCD sensors for bright fireballs, they will saturate, they will bloom, and they're not really useful. The new CMOS sensors, they're cheap and they do not bloom, and that's definitely what we should be doing now. We should kind of slowly switch. Another thing is domes. So up until recently, actually, we were using them in a global meteor network too, and then we realized that we should really ditch that because the astrometric quality that you can get is like 5 times worse than if you just put a flat glass. So what we have now is we have like a 3D printed thing where you just insert a flat glass, and that works wonders in terms of the improved astrometric quality, and also removes the reflections which might influence like the fireball location when you're doing the reduction, or any automatic algorithm is doing something to it. Okay, and finally, heavy video compression. We don't definitely need to save the raw data for fireballs. That's something that I guess we've kind of established in the last couple of years, but we can't really kind of take it too far and make the compression eat away the useful information. Okay, well, thank you so much.